I want to go a little bit further in the direction of making the nets a bit more complicated. And of course, the more complicated they get, the harder it is to make real mathematical precise statements. So, but at least we can go a little bit more in this direction and see at least what the kind of problems are which mathematically arise to make similar calculations like here. More interesting networks are, of course, if I'm starting to add layers and also non-linearities. Okay, so I mean I would look now on something where the function which I want to calculate, I mean in the last step still I do kind of linear regression, just a linear weighting, but before I should have maybe non-linearities. Okay, the non-linearity is usually also denoted by sigma. Sigma before was my variance, so but I hope it's clear from the context what I really mean. And then maybe I also had at least here one layer where I have a linear map W here. So yeah, okay, something like this. So I have here a matrix W, I have here non-linearity, and I have here small w. And so my function f goes from here to here. So here the RPs, my vectors or my data matrices, are mapped to, let's say, here an intermediate level, a hidden layer, which is m-dimensional, and then so this is a linear mapping, this W, multiplication by a matrix, but then I also usually allow this non-linear application of a non-linear function, the sigma, and then here I'm going down again to R. So this means the f of x is W sigma Wx, or if I'm putting in a matrix, a capital X, it's the same, W sigma Wx, where the sigma here is applied entry-wise to what I have here. Here I would have a vector, here I would have a matrix. I mean, the matrix is just a collection of the vectors which I get if I'm putting in several x's. Good, okay. Yeah, and now, I mean, if my net is essentially, again, usually only learning in the last level here, then this is still linear regression. It's only that now the linear regression is not directly done with the input vector, but with the vector which I calculate from it by first applying the W and then doing the non-linearity. So actually, I mean, I apply to what I get here, and those guys are usually called feature. So I'm working not on the input x directly, but on the random features which are calculated from this. So there are feature models or random feature models where I do here this stuff, and usually, I mean, those guys are chosen in a random way, so I do random calculations from this, and here I get something which are then my random features calculated from my data, and then in the final step I do the weighting. How do I weight the features to get the output? And if I fix this thing here, and this is not part of the training, then it's essentially just doing linear regression with what I get here instead of what I have here. Okay, so what one would have to understand, to make similar things as before, so what is the best W for describing this, is then actually that I don't need the distribution of my input data vector X or data matrix X, but the one which I get after applying those things. So this means I should, so here I get, so if I put in here my X, then what I get here is actually something, let me call it F, which is the feature matrix. So F is, I mean, it's what I get here. So this is F. So this is sigma W applied on my data matrix X, and these are my random features. Good. Okay, and now, so I mean, if I want to understand this, so I should understand what is the distribution of this matrix X. So given, let's say, X. I mean, the input data matrix, usually I model by a Gaussian matrix, and usually, I mean, the W here is also kind of usually, yeah, also a kind of Gaussian matrix. And the non-linearities, of course, there are also specific choices which I can do, but maybe I want to understand this in general. Okay, and so what I have here are essentially two things which I should understand if I want to understand this. So namely, first, can I understand if I'm multiplying my matrices? So it's not that I just want to understand one X, but now I have the product of two of them. So can I also understand them? And then, of course, can I understand what is the effect of taking non-linear functions of the entries of my matrix? So I mean, I have some matrix which maybe I understand, and then I take non-linear functions of the entries. So it's a very specific action on my matrix, and the action which is not a matrix action. I mean, if you have matrices, okay, you multiply matrices and you add them. That's the usual operations, which maybe you have the feeling you understand. But if you act with a function on the entries, what is this? This is going beyond the usual matrix theory. But that's the things which we should understand here. And so actually, I mean, these are two kind of problems which I probably want to address a little bit, maybe next week or so, but maybe now let me just point out again. So what do we have? We have two problems. Multiplication of random matrices. That's okay. That's something which is classical random matrix theory. So such things are known and one can deal with them. But then the second part, applying nonlinear functions to the entries of a matrix, this is essentially something new. This was not really considered in classical random matrix theory, because this is not an operation which usually you see in random matrix theory. Okay, and so this leads into something which maybe you can term a nonlinear random matrix theory. Which is maybe a new era or a new direction in random matrix theory, which is mostly inspired by the neural nets and questions around this, because there such things are used quite canonically. Okay, and maybe let me say that. Okay, so if I look on this. So this Wx, that's the classical thing, and actually this is something where we maybe have already some feeling what this should be. So maybe if I consider the first thing, so the first problem, so this means I would say my features are essentially I just take my data matrix and multiply it with some random weight. Some other random matrix. So I calculate random features, but in a linear way. Okay, so this is and let us assume that both of them are Gaussian matrices, which means that both W transpose and X transpose are Wishart matrices. That's the one which we understand, which have the Marchenko-Pastur distribution in the limit. But now I multiply them. And so what I would have to understand, if I do my linear regression, it's always the singular values of this f, or the eigenvalues of f times f transpose. So then what I would have to understand is f times f transpose, which of course is w x transpose times w transpose. And the question is, can we understand this? And yeah, I'm saying that actually this is not so far away from what we have done before, because this is essentially this effect of this W is the effect of changing the covariance of this Gaussian random vectors. So my matrix X are independent copies of a Gaussian random vector, and the Gaussian random vector usually has the covariance 1. Which corresponds in a limit to the Marchenko-Pastur distribution. But if I'm conjugating such a thing here, or you could say, I mean, instead of x, I consider now wx. I'm acting with a linear mapping on this, and we already have seen this in some exercises, that this really means we essentially changing the covariance of x. So we still have a Gaussian vector, but the covariance is now getting more complicated, and it's essentially given by conjugating with this W. Okay, so this means, what I have here is still kind of Wishart matrix, but the covariance matrix is not the identity, but it's more complicated. And this is actually something which in the last assignments you were also asked to look at. So namely to try to calculate the eigenvalue distribution of a Wishart matrix where the covariance matrix is not the identity, but I mean the covariance matrix has two eigenvalues, maybe 1 and 2, half of them are 1, half of them are 2, and you should try to derive an equation for this in the same spirit as we did it for Marchenko-Pastur. Okay, and this here is a more continuous version of this. So instead of just having two eigenvalues of the covariance, you have now more. Maybe in the limit you have a continuous distribution for this. But in principle, you can copy or imitate what you are asked to do in this assignment in this general situation. And you can derive some fixed point equations for the Stieltjes transform of this object. So the solution is not explicit anymore, because the equation which you get is not a quadratic equation, but it's just a more continuous version of this, which doesn't have an analytic solution, but you can use numerical methods to solve this. So I mean, in assignment you were asked to do this in a very, maybe not easy, but the simple situation like this to get a feeling for this. And this is maybe just making this more general and also more complicated, but in principle it works in the same way. Okay, so this is in principle something which, so this okay. So changing the covariance, let's say, from the identity to, let's say W transpose. Okay, and this maybe you should compare. So this is exercise 4 in the new assignment number 4. So there you are asked to do something like this. Okay, so maybe I can say a little bit more about this next time, but okay, I'm not sure whether it's worth this. But okay, at some point probably I should say more. But maybe let me now also just say how is it about the other thing. So if I take a non-linearity, and maybe if I not doing this on the product, but just doing this on the X itself. So how is the situation then? So I mean the second point, taking the non-linearities. So if I'm just doing this on our basic random matrix, then actually it's also something which is actually part of classical random matrix theory, because I haven't really changed the matrix so much. So if I consider F just as a non-linearity acting on X, I mean, X was our Gaussian random matrix, so all the entries had Gaussian distribution, and they were all independent. And now I apply a function on each entry, but of course this means I'm not changing the independence between the entries. I'm changing the distribution of each entry. I mean, they were identically distributed before, so they are identically distributed afterwards, because I change all of them in the same way with the same sigma, but I'm not changing the independence. So I still have a matrix where the entries are independent and identically distributed, but the distribution is not Gauss, but some other distribution. But actually, for those classical theorems, for like Marchenko-Pastur, actually, I mean, the Gauss distribution is not really important. I mean, I only formulated it in this way, and maybe at some points I use arguments which are easier if you do it for Gaussians, but in principle, everything works for a general distribution. So this means if I just apply a non-linearity to my Gaussian matrix, I get another matrix, but its asymptotic eigenvalue distribution is still Marchenko-Pastur. So in this case, as long as I don't destroy the independence between the entries, I mean, if the entries are independent and I just do entry-wise something, they are still independent. So I'm not changing the independence, and then this doesn't really have an effect. Okay, good. But so this means, I mean, if I have a matrix where the entries are independent, then the non-linearity or the entry-wise acting doesn't change anything. Okay, and so this means if I just do 1 for itself or just do 2 for itself without taking a product, I'm essentially still in the classical realm of random matrix theory. Then I know what happens. but they're nothing. Okay, I mean this. Okay, I mean both of them are non-trivial statements. That Marchenko-Pastur also is true more general, and that we can deal with the product of random matrices. Those are quite non-trivial things, but we know how to deal with this. Yeah, but now if we do this combination, then of course if I take the product, then in this product the entries are not independent anymore. Because they are combinations of different things. So they are dependent somehow. And then if I'm acting with a sigma, I'm changing stuff, and okay, I don't really, it's not so clear what I'm changing. I mean, you cannot say, I mean, things are dependent, afterwards they are still dependent, but okay, they might be dependent in some other way. So it's much harder to know what happens there. And this is something which was not really considered before. So those are things which now maybe in the last 10 or maybe 5 years were considered, because that's interesting things which we should understand for example, dealing with neural nets. But this is somehow enlarging the classical random matrix theory with new kind of questions which are a little bit outside. I mean, it seems we still can understand a couple of things, and maybe next time I want to tell you a little bit about what we can say about such things. So there are statements there, but one has to maybe, I mean, I'm not sure, maybe we can use tools which we have, but we have to adapt them and maybe use them in the right way. And maybe if we go more complicated, then maybe we really have to develop very new tools. But actually, I mean, there is evolving something which I like to call non-linear random matrix theory, which is trying to capture and deal with phenomena like this. Okay, and so maybe for maybe next week I want to go a little bit into this. Okay, but I think for today it's enough. I stop here. But okay, thanks.